Alright, so in this example, we're going to be integrating with respect to x, and we can see that here because the trig functions are a lot easier to deal with in their current form and not trying to solve them in terms of y. The challenge for a problem like this, though, is going to be determining exactly what the area enclosed is and finding those intersection points. So let's imagine that this appears on the section without the calculator, which isn't outside the realm of possibility. And let's see how we might deal with a problem like this, which is pretty challenging. The first thing we want to do is get kind of a rough idea of what this region might look like. So let's draw a graph. And we'll start with drawing sine x. So we know the maximum and minimum values for the two trig functions are going to be 1 and -1. And we know that sine starts at 0. And we know that sine is going to have a maximum at pi over 2. And another minimum, not a minimum, but it's going to hit the x-axis again at pi. So we'll draw that. We'll say our curve looks like that. X equals pi over 2 is a line that is vertical. X is always pi over 2. So it looks like we've got a start to our region. Y equals sine 2x is a function that's going to reach 1 faster. Its frequency is double. Or another way to think of that is if sine reaches 1 at pi over 2, then sine 2x is going to reach 1 at pi over 4, since 2 times pi over 4 is pi over 2. So we're going to have pi over 4 here. And this function is going to reach its highest point there and then come back down. So now we need to decide what's the region enclosed by the three curves that we were given. And that can be kind of tough. Let's start with the line pi, x equals pi over 2. So it looks like there's a region between the two sine curves and that line right there. And it looks like there's also an enclosed region over here between the two sine curves. In this situation, we're going to have to break the integral up into two parts because in this case, our top function is sine 2x and our bottom function is sine of x. And then once we hit this intersection point here, they change places. So our top function is sine x and our bottom function is sine 2x. So we're going to want to do this integral twice. We need to figure out where this intersection is taking place. And that's going to be the next tricky part. We'll know the intersection takes place when the two functions are equal to each other. So we can say, well, when is sine x equal to sine 2x? And that might not be immediately apparent to us. We could use a trig function. We could say we know sine 2x is equal to 2 times sine x cosine x. This might be easier for us to use since it's a product and ultimately we're going to be looking for zeros. And zeros are easier to find when you have products because 0 times something is 0. So if we plug that in, we're going to get sine x equals 2 sine x cosine x. And you might say, like, oh, hey, let's divide both sides by 0. or sorry, let's divide both sides by sine. But unfortunately, if we divide both sides by sine, we'll be removing an answer. And we could potentially be dividing by 0. One of the cases where these two are equal to each other would be if sine x is equal to 0. So you need to be careful when you divide both sides of an equation that you're not removing an answer, one of our two intersection points. So we can check real fast. Well, is sine of x and sine of 2x being 0, is that one of our solutions? And actually, yeah, our intersection point is 0, 0. So we already know that answer. So what we could do is we can say, all right, for any case that sine x is not equal to 0, we'll divide both sides by sine, and we'll get 1 equals 2 cosine x. And then 1/2 equals cosine x. And now we just need to know, where is cosine x equal to 1/2? And that's actually at pi over 3. So this intersection point here is pi over 3. So now we need to set up our integral. We're going to set it up into two pieces. Remember that for our first integral, sine 2x is on top and sine x is on bottom. And we're going to be moving horizontally, so we're going to be thinking of building this area with vertical rectangles and moving along the x-axis. So we're going to integrate from 0 to pi over 3. Sine 2x is our top function. Sine x is the bottom function. We're going to be integrating that with respect to dx. And then we need to add in the second region. So we're going to be integrating from pi over 3 to pi over 2, which is this piece here. And in this case, sine x is on top and sine 2x is on bottom. So that's our integrals. Now we just need to integrate it. The integral of sine is negative cosine. So we're going to have, in this case, negative cosine 2x. If we do a quick u substitution, we'll see that that's over 2. And then here we have negative sign, so it's going to be plus cosine x. This is going to be evaluated from 0 to pi over 3, plus, and here we're going to have negative cosine x plus cosine 2x over 2, and that's evaluated from, this should say pi over 2, pi over 3 to pi over 2. At this point, we need to be decent at remembering the trig circle, the unit circle. So cosine, we know cosine at pi over 3 is 1/2 because we solved for that. So that means that cosine of 2x is going to be cosine at 2 pi over 3. And then we're going to be dividing by 2. So that's actually going to be, cosine of 2 pi over 3 is negative 1/2. So this is going to be 1/4 plus, just sitting here and evaluating at pi over 3, we're going to have that plus, or sorry, these are, yeah, 1/4 plus 1/2. And then we're going to subtract 0. So in this case, cosine at 0 is 1, so we're going to have negative 1/2 plus 1. And we need to add in this other piece. Cosine at pi over 2 is 0, and cosine at 2 times pi over 2 is cosine pi, which is negative 1, so that's going to be negative 1/2. And then we need to subtract out and evaluate at pi over 3. So again, pi over 3, we're going to have negative 1/2 plus, and then that's going to end up being negative 1/4. And when we put that all together, we're going to get 1/2.